Okay, so let me just very briefly wrap up what we did last time. We're talking about calculation of the band diagram for photonic crystals, for two-dimensional photonic crystals, and also first Brillouin zone and important directions in the irreducible Brillouin zone. So this is the example of the triangular lattice photonic crystal in finite thickness slab, and there, as you know, we can produce photonic band gap, which means block propagation of light in a certain frequency region in any direction in plane. And last time we started deriving these main high symmetry directions, defining edges of the irreducible first Brillouin zone. So today I will just review that, and then we'll discuss a few more points. So then once you find these main directions, defining edges of the irreducible first Brillouin zone, as we discussed previously, and it's sufficient to calculate photonic band diagram along those directions if you're interested only in the extreme points of the band diagram or band edges. And that's what's plotted here. For certain classes of applications, if you're thinking, for example, about refraction or super prism devices based on photonic crystals where you're using propagation using guided modes or guided resonances of photonic crystal, you have to calculate band diagram for also all the points inside of the irreducible Brillouin zone. But you know that if you have it for the edges and all the points inside of this little triangle that we'll review in a moment, then you have a full set of block states, and you can expand any field inside of the propagating through such a periodic structure in terms of the block modes. So now there were a few things that I'd like to review. One was irreducible Brillouin zone. We will review that in a moment. The other was light line, which we will also review in a moment, and you'll play with this as well in your homework. And the third thing are the electric and air band modes. So each point inside of the band diagram that you have here is a mode that can propagate through this structure. Each point also has a form of two-dimensional block state, and you see here for two particular points in the band diagram, you see the electric band and air band, which concentrate electric field in high and low index regions respectively, as we proved using electromagnetic variational theory. So here is a brief review of the material we went through last time, right? So this is for triangular lattice, calculation of the irreducible Brillouin zone and reciprocal lattice. And this is a very simple geometry. I mean, it's something that you can repeat easily for other types of lattices. In this class, we will primarily focus on two-dimensional photonic crystals, and of course, one-dimensional are even simpler, but you can use the same procedure also for three-dimensional lattices. There are three-dimensional photonic crystals, as we'll discuss later, but they are very difficult to fabricate and don't have very good properties. There are a lot of imperfections, and they have more loss than two-dimensional photonic crystal for that reason, although theoretically they shouldn't, which is the reason why we will not really spend much time analyzing three-dimensional lattices here. Okay, so going back to triangular lattice, this is a cross section. Here we show rods embedded in some material with refractive index epsilon 1. It doesn't matter, it could be holes or rods, it's not important. Calculation of the lattice is exactly the same. You have to find primitive lattice vectors, which here are these two vectors with the same length and angle of 60 degrees between them, and this is how they're described in the XY plane. And then you plot KX, KY plane, actually directions KX and KY in the reciprocal space are lined up with directions in X and Y in real space. And then you use this very well-known relation between reciprocal lattice, primitive reciprocal lattice vectors B1 and B2, and real space lattice vectors A1 and A2 to find B1 and B2. And it's clear that, I mean, you can actually pick B1 to be orthogonal to A2 in this direction, and B2 to be orthogonal to A1. So these two vectors here have 120 degrees angle between them and length of 4 pi over root 3a, which you obtained from the Kronecker delta relation. And if you have two vectors that have the same length and 120 degrees angle between them, then they also describe triangular lattice in reciprocal space. But triangular lattice, which is rotated relative to real space by 30 degrees. So what do I mean by that? Well, if you look at the nearest neighbors in real space, right, they would be aligned in the direction along the x-axis and also 60 degrees direction. If you look at the reciprocal space, nearest neighbors would be aligned up at 30 degrees and also 90 degrees. So that means that reciprocal space lattice is rotated by 30 degrees relative to real space lattice. And this is something that we also often plot in the, when we line up irreducible Brillouin zone relative to real space lattice. We'll go back to that later on, right? So then you have light vectors B1 and B2, you know, they define reciprocal space lattice. Then you find, as we discussed last time, first Brillouin zone by plotting perpendicular bisectors to nearest neighbors. That defines hexagon. That has much more information than what you need, because by symmetry, each triangle, equilateral triangle in that hexagon is the same, contains the same block states, and then each half of this equilateral triangle contains also the full information of block states. So what it's enough to just take one of these triangles, which are 1/12 of the hexagon. And that's what we typically define as gamma, x, and j direction. But you can pick any of these triangles here, and you would actually obtain exactly the same block states. So this is the one that I picked here, but you could have picked the one that goes downward or the one that goes here. Any of them would contain exactly the same block states and produce the same Venn diagram. Okay, any questions? Okay, so then if you look at this triangle, right, just from simple geometry, you can define what gamma x is, what xj, and what gamma j is, right? And you see here, for example, that gamma j is lined up along the height of the equilateral triangle in reciprocal space, but since real space and reciprocal space are rotated by 30 degrees relative to each other, that would be along this direction, like x direction or 60 degrees direction in real space, right? So if you go back to the Venn diagram, this is exactly how we plot gamma j here, right? So gamma j goes along the nearest neighbors, and then gamma x would be along the height in real space, which is in reciprocal space along the nearest neighbors. So you can draw the irreducible Brillouin zone or Brillouin zone in the real space lattice. You just need to keep in mind that they're rotated relative to each other by 30 degrees, and that kx and ky directions are lined up with x and y directions. So once you have irreducible Brillouin zone, one of these triangles, and let's pick this one, you can define these three directions. Then you calculate block modes for all of these directions, and typically you use numerical methods. The Venn diagram that I showed you before, and that we'll show again, is calculated using finite difference time domain method. Here it is. So what you do is, let's say, pick gamma x direction, which means that kx is 0, and then you change ky going from 0, 0, gamma is always 0, 0, to x point, which is defined as 0, and then a value that we define for x. And then you can actually numerically kind of split this into different segments. We here split it into 10 or 12 different points. For all of them, kx is 0, ky changes in these increments, and then we apply block boundary conditions at the edges of the unit cell. And we look then for what frequencies are supported for that particular combination of k vectors. And that's how you, after your Fourier transform, you obtain all the points that are supported in the Venn diagram for particular combinations of kx and ky. And here I did shade the points above this light line, which we'll also review in a moment. There are modes there as well, but we didn't care about them because they're called leaky modes for the reasons that we'll also review in a moment. Any questions? Okay, so then we're going through a little bit longer introduction just because we had the whole weekend and 4 days until now, and this is also something that's very important for everyone to understand. So solid line is light line, right? Light line is defined using dispersion relation for free space, right? So, but only looking at the values of the k vector that are plotted on the horizontal axis. Of course, in space, there are three possible components for k vector, kx, ky, kz, but on the horizontal axis, we only plot kx and ky, which is why light line is defined as omega over c squared is kx squared plus ky squared. Or in other words, if you look at this photonic crystal slab, something incident from free space on that slab would have to be above the light line because it would have to contain non-zero and zero or real kz component. So kx squared plus ky squared plus kz squared would have to be above this line. That's why everything above this line can be incident from free space or can couple to free space modes, right? Because it would have real kz. And this is why we refer to this region as leaky modes, because it means that if you have some discrete modes, and you do have discrete modes that are continuation of these modes below the light line, above the light line, they would be able to couple to free space modes and they would leak. So they would be lossy. If you are interested in propagation in photonic crystal, you prefer to operate below the light line because to be below the light line, you need to have kx squared plus ky squared less than this omega divided by c squared, which means that you need to have kz, which is imaginary, right? And imaginary kz means evanescently decaying outside of the slab and total internal reflection confined. Is this making sense? Okay. So now every point here in the band diagram is a block mode. Of course, we're plotting two-dimensional k vector on the horizontal axis, and this is two-dimensional periodic structure. So block modes are two-dimensional block modes, right? And here is how they're represented. You have a periodic part, u of x, y, which would be periodic with periodicity of the lattice, of triangular lattice. And then you have a plane wave, and in the plane wave, you have kx and ky that describe particular point that you read on the x-axis here. And of course, this periodic part also depends on the k, or it varies primarily from band to band, right? So now when you look at the band diagram, here I plotted electric field distribution for two particular points, two particular frequencies at the x point. X point, again, has kx equal to 0, ky has some fixed value, ky direction is along the height of this triangle in real space, right? So that's your gamma x. It's along the height. So that propagation in the gamma x direction would be propagation along these heights of the triangle. And that's indeed what we see from the field profile here, because red and blue are positive and negative for the field. But what is different between these two, right? I mean, although they both propagate like waves in the gamma x direction, both here and here, and they have the same periodicities, which means separation between blue and blue for both of them is a √3, two heights of the triangle. And that's expected because they have the same kx and ky combination. The bottom one, the electric band mode, has electric field concentrated in high index region, and air band mode has electric field concentrated in the low index region. And that's also what we expect from the electromagnetic variational theorem, okay? If I asked you, for example, to plot electric field distribution that you guess for the J point of the band diagram, how do you think that would look like? Any thoughts? J point, right? So this point here, what would you see?
Degeneracy.
Here, actually, no, I'm not asking about that, about degeneracy. I'm just asking how the electric and air band modes would look like, right? So where is the propagation in the gamma x direction, right? Is kind of like along the heights of the triangle. Gamma j direction in with real space lines up along the direction connecting nearest neighbors, right? So you would see some wave fronts, right? But those wave fronts would be oriented how?
Like they'd be diagonally?
Yes, yes, they would be diagonally, and they would also, I mean, because that's your gamma j direction, right? So you would have some wave fronts that would go like this, right? And then they would be, for the electric and air band, different how? They would be, again, like for the x point, misplaced relative to each other, so that one overlaps more with air and one overlaps more with electric. Is that making sense? Okay.
Yeah.
Yeah. Any questions? So I'm mentioning this because this is giving you an idea how you can already guess mode symmetry for particular points even without calculating the field. I mean, these ones are very easy to guess. When you go to higher bands, then you have more oscillations in the electric field, so it gets a little bit more complicated. But here, simply by looking at the plane wave distribution and assuming that this part is almost constant, you can actually see how the fields would look like for the electric and air band modes. Okay? Few more points, right? So we said everything above the light line would have to have kz, which is real. Sitting on light line would be kz0. A real kz means going above the light line. Below the light line would be imaginary kz, right? Because this whole thing then would be less. Kz squared would be negative, and this whole thing would be less than omega light line divided by c squared, right? So if you are interested in using guided modes of this structure to really guide light in photonic crystal without loss, do you pick modes above the light line or below the light line?
Below the light.
Below the light line, right? Because below the light line, you cannot really couple. I mean, kz inside of these modes has to be imaginary, which means evanescently decaying in the vertical direction. So you are not really coupling efficiently for two free space modes, as opposed to something that's here that has real kz and couples really well to free space modes. Okay. So above the light line, that means that all the states that are above the light line could be excited from the outside, right, with a laser. So if you take your photonic crystal and shine a laser and twist the angle of that laser, will you be able to couple to something here below the light line? Not really, right? You can only measure the states that are above the light line, right? Because you are not coupling here. Your kz below the light line is imaginary. But you can actually probe the states above the light line using that. And if you were interested in, for example, designing something that would have good light extraction, like light emitting diode, right? Or surface emitting laser, you would also use these states that exist above the light line, because that would couple efficiently to real kz's. You would extract light outside into the light cone, right? And that's the loss that you would like to have from the system. If you're just interested in guiding light without loss, then you want to operate below the light line. Does that make sense? And when we talked about total internal reflection, you know that something confined by total internal reflection has exponential decay vertically. Exponential decay means imaginary kz. So that means you're below the light line. Okay. So this is, of course, for guided resonances. We'll talk more about resonators later on. Just a review of what we already discussed, right? So guided modes below the light line, confined by total internal reflection, imaginary kz. Those are the modes that you use when you want to have low propagation loss. Above the light line, there are discrete modes that you would use if you would like to have good extraction efficiency. And they're called leaky modes, right? But I'm just shaded them over here. Any questions? Okay.
Is it possible to have a mode that link with the leaking mode and the guided mode?
That links them, you say?
Yeah.
We actually, I mean, the system is not perfect. What I was just, these modes below the light line, in ideal case, don't couple to modes above the light line, right? But whenever you have some sort of scattering inside of the structure, then you would also couple to free space radiation mode. Also, for example, if you have some very small periodic perturbation of the structure, right? So you start from your hexagonal photonic crystal, but let's say you modulate in certain direction, let's say in gamma x direction, right? I mean, in gamma x direction, we modulate every other period. So the ones that blue is lined up with, I slightly increase holes, right? What that would do is it would fold back these modes above the light line. So the states that are below the light line would be folded above the light line just by a little bit. It's kind of, you know, the discussion that we had from master equation when the band gap opens. In that case, you're starting to kind of slowly open the band gap at the middle of gamma x, right? And these points that are below the light line would start scattering above the light line. So the answer to your question is, I mean, any imperfection would scatter light and couple free space modes and those below the light line. So low loss or no loss means only in the ideal system. And also to couple modes below the light line and above the light line, you can start introducing some very small perturbation in the structure. Right? And that starts folding the zone and scattering the modes above the light line. Right? But if your perturbation is very small, then you are not really completely folding and opening a large band gap, you're just coupling them a little bit. Okay.
Yep.
That if you are interested, there is also a concept of coupled cavities and coupled cavity arrays, which is related to this folding of the Venn diagram. Okay, so now just going back to one additional thing, I sort of cheated when I showed you this Venn diagram because this Venn diagram is calculated only for 1/2 of the modes inside of this photonic crystal. If you have vertical symmetry, and this is calculated for finite thickness photonic crystal, right? So this is a slab of silicon surrounded by air. But you can separate modes into two different categories there, which we call TE-like and TM-like, or vertically even and vertically odd, that I introduced in a moment. And only vertically even modes have a photonic band gap for this particular type of lattice. Vertically odd or TM-like, they don't have a band gap for triangular lattice. And I'll explain you in a moment what that means and how we define that symmetry for photonic crystals. But what that also means is that you have to be very careful how you launch modes into your structure, because if you want to benefit from the photonic band gap, it would work only for a specific polarization of the excitation, because the other polarization would have no band gap. It is possible to control that. I mean, you can control it if you do passive excitation of the structure by lining up input field polarization from your laser relative to the modes. Or if you're building active structures like lasers, you can also, we'll talk about cavity QED and light matter interaction pretty soon, but you can pick your quantum val region or quantum dots in such a way that dipole orientation from your emitters in the material is primarily oriented in the direction that couples to one specific polarization. And that way you kind of eliminate the other polarization, and you can employ the structures that only have interesting properties such as band gap in one polarization. And you'll see very high quality factors, for example, built for these triangular lattice photonic crystals. But keep in mind, it's only in one specific polarization where there is a photonic band gap. So how do we define these categories of modes? If the structure is vertically symmetric, and this one is vertically symmetric because you have air on top and on bottom, we can separate modes to two categories, TE-like, which are also referred to as vertically even, and TM-like, which are referred to as vertically odd. And they're defined relative to z equal to 0 plane, so that's center of the slab. If you have asymmetric structure, if you have, for example, oxide underneath, and this is silicon, and on top you have air, then you don't have vertical symmetry, right? Structure is not vertically symmetric, which means that these two categories of modes can mix, and that can introduce losses in the system. But if you don't have if you still have a large contrast, as you do if you have oxide underneath, because it would be 1.5 and this is 3.5 and air would be 1, right? They're still primarily TE-like and TM-like. But keep in mind that they're not exactly decoupled from each other unless you have vertical symmetry, which is why it's generally really good to make sure that you have vertically symmetric structures if you're making high Q quality resonances. Because if your structure is not vertically symmetric and your modes mix, remember that you only have a band gap for TE-like modes, you don't have it for TM-like modes. Inside of the band gap where you're building your resonance, you will be able to couple to TM-like modes, right? And you will actually reduce the Q factors in general case. So how are TE-like modes or vertically even modes defined? TE-like modes are exactly TE at z equal to 0 plane at the center of the slab, okay? And for photonic crystals, what is TE and TM depends on which electromagnetic structure you're looking. For photonic crystals, if these were infinite rods of air inside of some slab or completely two-dimensional structure, TE would be, you would have exactly TE and TM modes. And TE would be electric field transfers to these rods, right? So that's what it means. And TM would be magnetic field transfers to rods. So for TE means that electric field is in plane XY plane, transfers to rods that go in the Z direction. But as soon as you have finite thickness structure, and you always have finite thickness structure, there are no infinite rods of anything, or two-dimensional photonic crystals in real world, right? Then this TE and TM only holds at Z equal to 0 plane. Only in Z equal to 0 plane, for TE-like modes, you will have electric field having only X and Y component and 0 Z component, right? But as long as you move from Z equal to 0 plane, you have all 3 components for electric field and all 3 components for magnetic field. This is why it's called TE-like and TM-like, right? Because it's TE or TM only at the central plane. Is that making sense? Okay, so then, you know, maybe what makes more sense from the symmetry direction, I mean, this TE-like and TM-like, that's just coming from what is called TE or TM for two-dimensional photonic crystals, right? So TE means electric field perpendicular to rods in XY plane, right, at the center of the slab. TE-like modes are basically vertically even modes. And vertically even means that they exhibit even mirror symmetry relative to mirror that is positioned at Z equal to 0 plane. TM-like modes are called vertically odd because they exhibit odd mirror symmetry relative to Z equal to 0 plane. And I'll explain that to you in a moment, right? Away from Z equal to 0 plane, which is center of the slab, you have all 6 field components, 3 E field components, 3 B field components. At Z equal to 0 plane, for TE-like modes, you have only E field in the plane, EX, EY, and then from Maxwell's equations, that means that you can have only HZ, Z component of magnetic field. And for TM-like modes at the central plane, you have only transverse magnetic field, HX, HY, and EZ in the Z direction. So again, TE-like is vertically even, TM-like is vertically odd. What does that mean? So mirror, I mean, this is what mirror operation, how mirror operation is defined, but it's basically obvious. So if you have a vector and you have a mirror at Z equal to 0 plane, the way this mirror would map a vector is as shown here, right? So mirror operation, mirror at the Z equal to 0 plane, applied to an arbitrary vector E, would flip EZ component, but since the mirror itself is in the XY plane, then EX and EY components are untouched. Does this make sense? Right? So mirror applied to arbitrary electric field vector would flip EZ as shown in the picture, right? But EX and EY are untouched. Even mirror symmetry means that a vector is an eigenstate of the mirror operator corresponding to eigenvalue 1. Okay, so here is what it means. So even mirror symmetry means that electric field is an eigenvector of a mirror operator corresponding to eigenvalue 1. Okay, so this is an eigenvalue equation. This is electric field, and this sigma z is eigenvalue of 1. So let's plug that back in, right, into this equation. Mirror operator applied to electric field flips EZ component. If our electric field is an eigenvector of the mirror operator, then this has to be equal to this, okay? In order for this to be equal to this, EZ has to be equal to 0, because you cannot have minus EZ being equal to plus EZ, okay? Which means that EZ has to be equal to 0 at the mirror plane. And that's what even mirror symmetry means. And that's what our TE-like modes mean, right? They are vertically even, meaning that they are eigenvectors of mirror operator with eigenvalue 1, right? So they have to have EZ equal to 0 at the mirror plane, meaning that at this plane, they only have EX and EY. Does this make sense? Okay, and then odd mirror, which is the same as TM-like modes, means that electric field is an eigenvector of the mirror operator corresponding to sigma z equal to -1. So if you go through the same simple calculation, that means that mirror operation applied to electric field vector is the same as negative of the electric field vector, but that means that EX and EY have to be equal to 0, right? Otherwise you cannot have EX and EY being equal to negative EX and EY. And that means that both EX and EY have to be 0 at the mirror plane. So the only electric field component that you have is EZ, okay? So for TM-like modes or vertically odd modes, and you can see in the literature, people are referring to TM-like modes as vertically odd modes, the only electric field components that you have is EZ. Okay, and of course, as you move from the mirror plane for these finite thickness structures, you have all the field components. So the important message is that for this lattice type, and likewise for the square lattice type, only vertically even modes or TE-like modes have photonic band gap, which means that at the central plane, for the modes that have a photonic band gap, you will actually have to excite electric field in plane, in the XY plane, okay? Or for the modes that are propagating here outside of the band gap, they would also have electric field in the central plane polarized in the XY direction, okay? If you put your quantum well here, which has dipoles that are oriented in the Z direction, okay, that would be, for example, tensile strain quantum wells, for those of you who work on quantum wells, right? They would have also dipole orientation in the Z direction. Even though you picked your quantum well at the frequencies that are inside of the photonic band gap, like here, right? There is no band gap for TM-like modes, right? So if your dipole can couple to the Z polarization, that would couple to some propagating modes and leak, okay? If you would like to use this to build a laser and form some sort of resonator by removing some holes from this mirror, and you pick your quantum well with a frequency which is inside of the photonic band gap, your resonator will work only if your dipole orientation is such that is inside of the photonic band gap for TE-like modes, right? Which means that your dipole has to be in plane. Does that make sense? Yeah, if your dipole is out of plane, there are here modes that we didn't plot, the other half of the modes, which are TM-like modes, and they would couple to Z orientation of electric field. So keep that in mind, right? I mean, that's not really too detrimental because you can always be careful in terms of what you're exciting in the structure and how you're exciting the modes. But keep in mind that all the Vegas that we'll be talking about and resonators and everything is for vertically even or TE-like modes, okay? We don't really even plot band diagrams for TM-like. So a few questions for you now, just to review this. If you take this photonic crystal, you make it out of silicon, let's say, and I mean, the one that I plotted here is for the one that's surrounded by air or vacuum on top and bottom, right? What happens if you immerse it in water or you fill it up with oxide, right? You deposit oxide everywhere around this photonic crystal. Where would the light line be? Where would this light line be? And just as a hint, light line means separation of the modes that are guided inside of the slab and those that can leak out of the slab and couple to free space, right? So free space, what is different between something that's surrounded by water or oxide, which has refractive index 1.5, and vacuum, which has refractive index of 1? Those free space modes are different, right? Which means that light line has to be positioned at a different location. But where is it positioned?
It would be angled like lower.
Exactly, it would be angled lower because the speed of light differs, right, in these two media. And here, I mean, if you look at the gamma X direction, for example, what we're plotting is basically you only for gamma X direction have ky, you don't have kx. So you're basically plotting ky squared. Omega is equal to ky times c, right, for this light line. But if material is not vacuum surrounding photonic crystal, but instead is something with refractive index n, like 1.5, then the light line would be omega is equal to k times c divided by n, right? So as you just said, and sorry, I forgot your name. Can you remind me your name?
Peter.
Peter, yes. Peter, who is in Netherlands still, right? If you look at the light line, in that case, it would be actually lowered by n here, right? So it would be c over n, which means that you have larger number of modes that you can couple to and leak to, right? And you have to be careful about it because it would cut through this region, and some of these modes that were previously confined and not leaky would be leaky now, okay? So that's important thing to keep in mind, that light line depends also on what's surrounding your material. And also that for the same reason, when you're defining, when you're surrounding material with something that has a lower refractive index, you're increasing the number of free space modes around the material. So you have smaller range of K vectors here where you can define your resonator, right? So in general, when you have refractive index different from 1 surrounding your photonic crystal, as you'll see later on, it will be a little bit harder to make high Q resonator. It's possible, but it's harder because your light line is pushed down, so you have smaller space where your modes can be confined. Any questions?
Yeah. So there basically is like less space for the bands to be in, but is the shape of the bands like altered also by the medium around the crystal?
If you just change it from 1 to 1.5, it's not a very large perturbation. I mean, we'll just discuss that also for changes in other parameters in the material in a moment on the next slide, right? If you're not changing lattice and you just make small perturbation or refractive index, it's not really significantly changing, except that you are changing the light line and you're changing frequencies of these modes, right? They're also changing and moving, but you're not dramatically changing the shape of the bands. They're more or less the same. But more significant perturbation would start changing them significantly. I mean, I'll discuss that in a moment now. So just one more thing before we wrap up this part. So here, again, we're showing photonic crystal for this triangular lattice below the light line, numerically calculated, right? And this is calculated for a specific choice of parameters. And there are a few parameters that define properties of the photonic crystal. I mean, of course, lattice type is important. And again, this is only for TE-like modes or vertically even, where you have photonic band gap. Lattice type is important. And here is triangular lattice of air holes inside of the slab with refractive index 3.4, right? Slab thickness is important. Hole radius is important. That's R, and A, which is the periodicity, okay? If you change lattice type, if you go to square lattice, it would look very different. You can open a band gap, but generally it's much smaller. But also if you don't change the lattice type, if you keep the same refractive index, but you change A, like periodicity, or R, or you change thickness, you take your slab and you start depositing, spinning some material on top, you will change photonic band gap, right? And here on the right, we're showing the size of the photonic band, or band gap, which is basically the peak of the dielectric band to the bottom of the air band. So the separation between these 2 points for different parameters, right? Also numerically calculated. So vertical axis is normalized frequency. There are pairs of lines that correspond to this top of the dielectric band, bottom of the air band, right? So for example, the stars correspond to bottom band, dielectric band for different parameters, and circles correspond to air bands for different parameters, okay? And we're just plotting the size of the band gap. On the horizontal axis, you have normalized thickness, which is thickness of this slab divided by periodicity, and different pairs of lines correspond to different hole radius divided by periodicity, R over A, okay? And you're keeping N of 3.4. For the range that's studied here, and that goes back to Peter's question, we're not really changing structure of the band diagram dramatically. So it remains the same shape of the bands, except that they're pulled up or down, right? And band gap is changing, but shape of the bands is not changing dramatically. It's still a small perturbation. But as you can see from this plot, you're changing the location and size of the band gap. So why are you changing it? So maybe we can have a discussion, or maybe you give an answer to why things are changing the way they're changing. So let's pick certain fixed R over A, right, of 0.3. So R radius divided by periodicity is 0.3. So this pair of lines, this and this. What is happening as you're increasing D over A? Meaning you take that slab, you fabricate R over A 0.3, photonic crystal, triangular lattice, and then you go to clean room and start depositing using layer deposition, for example, extra material on top of your slab. Or you start thinning it down, which would go in different direction. You're just slowly etching it with the reactive ion etcher. What is the trend, right? I mean, for this range of D over A, band gap size is not really changing dramatically, right? But what is changing is that the whole band gap frequency goes down, right? As you're making the slab thicker. Does that make sense? Why is the band gap in frequency going down? That means both the electric band is going down, right? Frequency of the dielectric band is going down, and frequency of the air band is also going down, right? Right. Why is that happening? As the slab is getting thicker and thicker. And maybe a hint, right? Remember variational theorem? If field overlaps more with high index region, what happens with its frequency? Goes down, right? Like the electric band mode. More overlap with high index region means the frequency goes down. So if you take your slab and you deposit just a tiny bit of material on top, you are not going to perturb how electric field looks like, right? The only thing that will change is that if you look in the vertical direction, evanescently decaying field, it will overlap with more high index region. And from variational theorem, that will pull the frequency down, as you're seeing here. Is that making sense, right? And opposite direction if you're thinning it down. Now, another question for you. If you're increasing R over A, right? So if you go from hole radius of 0.3 times periodicity to hole radius of 0.4 times periodicity, same lattice, same thickness, what is happening with the band gap? Frequency goes up, right? For both of these, the electric band goes up, air band goes up, and band gap size increases. Okay? Right? So first, why is this happening? Why is the frequency of why is the whole band gap going up? And why is the band gap size increasing? And it's the same thing that we said to use to explain the other trend, right? If your hole radius is increasing, you're increasing the overlap of the field with air, right? So if you just tiny bit increase hole radius, you're not going to change significantly how electric field pattern looks like, but you are going to increase the overlap of that electric field pattern with air, which means that the frequency should go up. And now final question, why is the frequency of air band mode perturbed by more, jumping by much more than the frequency of the electric band mode? You see the jump as you increase R over A from 0.3 to 0.33. This is the jump is, I hope you see my pointer here. The jump for the electric band mode is much, much smaller than the jump in the air band mode. Why is that the case? Any thoughts? And for that, you can actually just go back to the field patterns that we have.
Does it have to do that like proportionally? Like the air band, if you increase the size of the hole, like how much more it is in air doesn't change that much. Whereas the dielectric band is like mostly like not in the air at all. So if you increase the hole, then proportionally it will affect it a lot more.
Absolutely. I mean, it is related to what Peter just said, right? So the electric band has electric field, which is primarily in the electric, as you see here, right, on the band diagram. And air band has field that's primarily in air. So as I start increasing these holes, which, I mean, these are zeros of the field lining up with holes, and these are maxima of the field lining up with holes, right, for the electric and air band. So as you start increasing the holes, the perturbation on the air band would be much, much larger than perturbation initially on the electric band, because you're actually cutting it through zeros. That's exactly the reason why this is jumping much more for the air band than for the electric band. Okay, does that make sense? Yeah. Okay. So anyway, I mean, this is showing you that you can control the position of the photonic band gap and frequency by controlling parameters of the photonic crystal, which is what, I mean, if you are making photonic crystal and you're doing fabrication, you generally, fabrication is not always perfect, right? I mean, you, for example, want to fabricate holes with certain radius over periodicity, but you go to the lab and depending on how etching worked out or electron beam exposure, you may be somewhere else, right, in this space. Which is why in general, it's always good to do, for example, dose arrays. You take one chip and then you make change dose during electron beam lithography if you're using electron beam lithography, which kind of spans the whole range of Rs, right? Because different doses, increasing doses means that you would increase radii. And then you also, after the fact, after the processing, can also do post-processing to control properties by some etching or deposition of the material and so on. And one more comment, before we make a break. I asked you also, I mean, of course, photonic band gap is increasing, position of the dielectric band is increasing, and position of air band is increasing even more if you are increasing hole radius, but band gap size is also increasing, right? How can we explain that band gap size is increasing as you're going to larger R of array, right? So if you go to R of array of 0, would there be a band gap? R array of 0 means no holes, right? And they're vanishing, right? You have to start increasing them to introduce perturbation and start opening band gap. And even the little holes would not be enough to open band gap for all directions in the XY plane, right? You have to get somewhere around 0.25 or R of R array in order to open a band gap. But typically we work around R array of 0.3. As you're increasing R array further, all the way to 0.4, this band gap size is increasing. Why is it increasing? I mean, you're basically increasing your perturbation more and more, right? If you're going back to our master equation analysis, that means that you are increasing the size of the harmonics, right? Your Fourier components in your epsilon distribution are increasing as you're increasing perturbation. And the size of the band gap is proportional to your Fourier components in epsilon that are getting larger and larger. Or when you're looking one-dimensional distributed Bragg reflector, higher contrast means higher stop band of the mirror. And when you get to R array of, I mean, you can't go infinitely here, right? That's the maximum R array that you can have here.
0.5.
0.5, exactly, right? Because when you get to 0.5, holes start touching, right? And of course, in real life, if this is a suspended structure, it would collapse. But even if it's not suspended structure, you have instead of having holes, you'll start having the electric rods, right? And that's a very different lattice type from array of holes. All of these bands will be very different in that case. Does that make sense? Okay. So we prefer to work somewhere around 0.3. It turns out that when you go to 0.4, you have larger photonic band gap, but then for resonators also you end up scattering more outside of the photonic crystal and having lower loss. So range around 0.3 seems to be the optimal range for especially high Q resonators, and you'll see that later on. And then vertically, this thickness, here it's fixed and it's picked to be again, between 0.35 and something like 0.65 of the periodicity. This is a normalized frequency, A over lambda. Generally, thickness, I mean, you can also see that from this whole plot, but the rule of thumb is that you pick thickness of the slab that would only support single mode propagation if this was just a slab waveguide, right? Which means that thickness of the slab should be on the order of 1/2 wavelength in the material. Okay, so if you, let's say, are building something to propagate at 1550 nanometers, right? You will pick 1550 nanometers divided by refractive index of silicon or gallium arsenide or whatever material that you're using, which is divided by 3.5, and then 1/2 of that, right? So it's 1550 divided by 7, which ends up being somewhere around 200 nanometers or 250 nanometers. Right. So when you look at the photonic crystals pictures that I showed you before, they generally have thickness of around 200 to 250 nanometers if they're built for operation and telecommunication wavelengths. Right. So that's the rule of thumb. You want to be in the single mode regime vertically. If it's not in the single mode regime, I mean, all of these modes that you produce here in the photonic band diagram, they originate from slab waveguide modes, right? Just folded back by symmetry of the holes that you etch in photonic crystal. So if you start from multi-mode waveguide, I mean vertical direction, something that's way too thick, then this would be also much more complicated because there would be these multiple modes of slab waveguide folded back and forth. Okay, so we pick single mode operation vertically, 1/2 wavelength, and then we also can control for that region of thicknesses. Right, we can control the position of the band gap by picking radii and periodicity and changing thickness of the slab. Okay, so now that's all I wanted to add. We'll make a very brief break, and then after the break, Raul will start the discussion of the coupled mode theory. I'll be online. Okay, and if you have any questions, I'm happy to pick them up during the break.
Professor, I have a question about the X gamma J notation.
Yeah.
They're not like universal notation, right? I mean, there can be, of course, other types of lattice, right?
Of course, yes. Are you talking about notation gamma X, gamma J, those directions?
Yeah,
right. Yes. And even for this type of lattice, sometimes you may see people use different letters to label the same directions. So it's not really, universal notation. I mean, sometimes for gamma X direction, sometimes people use gamma X and gamma M for directions, even in triangular lattice, although that's more typical for the square lattice.
So you always have to like state what each terms are for if you are using a photonic crystal.
Yeah, I mean, if you're using photonic crystal, of course, Brillouin zone, right, is always defined in the same way. So if you start from triangular lattice, it's always the same Brillouin zone. You may just use different letters to label different directions. But what's typical is that when you plot your band diagram, you show your irreducible first Brillouin zone lined up with your real space, like I showed. Remember gamma X J triangle? I showed it lined up to real space photonic crystal. And that way people know exactly which directions you're talking about. But lengths of the vectors are always the same.
Okay.
Does that make sense? Yeah.
Yeah, so that kind of like the irreducible Brillouin zone is always like plotted as an inset or something? Yes.
So that then you know what you're talking about. Yes, so that people know what you're talking about, right? But lengths of vectors are always the same. And of course, I can take that same irreducible Brillouin zone and take any rotation, like 60 degrees rotation of that, and it would be the same thing, right? Because the underlying photonic crystal has, for the triangular lattice, 60 degrees rotational symmetry. Right. So if you plot it in any direction rotated by 60 degrees, it's fine. But it's important to show it superimposed to the underlying photonic crystal so that people know how your directions are labeled.
Okay.
Okay, thank you. I'll let Raul talk now.
Hello, can you hear me? Yes. Okay, excellent. Should I start or should I wait for a bit? Okay, I guess I can start.
Yeah.
Okay, so what I'll do over the next 1 to 2 classes is basically very quickly go through chapter 3 that I've uploaded online. So it's on temporal couple mode theory. So couple mode theory is a very, very useful tool in analyzing cavities, coupled cavities, systems of cavities and waveguides and so on. And you'll probably, if you read like a lot of papers in the field of nanophotonics with cavities, and even fields like nonlinear optics or quantum optics, in which we are trying to use cavities in different applications, you might come across people using couple mode theory in order to analyze and simulate the cavity system. So I thought it would be a good idea for us to go through the basic formulation of the subject. It's actually very simple. It's like a model building exercise. So one of the motivations of couple mode theory really is to build a circuit model for nanophotonic systems, right? So if any of you have done electrical engineering classes, so you know that you have these complicated electrical circuits, and you can of course go and solve Maxwell's equations for these complicated electrical circuits and analyze them exactly. But that's a very, very inefficient way of going about studying these circuits. And not only is it computationally difficult, but it also doesn't really give you any intuition on how those circuits behave. So what you almost end up doing when you're trying to understand how these complicated systems behave is build like simple models for your individual components, and then have a more complicated model for your entire system. And that essentially is the goal of couple mode theory as well, right? So for example, over the last few lectures, and Yalan has talked about how you would go ahead and design these cavities so you can understand these cavities with electromagnetic simulations. But if you have a bunch of cavities coupling to each other, or you have a bunch of cavities and waveguides that are coupling to each other, you wouldn't want to do like a full-blown electromagnetic simulation of the whole system. But rather what you would like to do is do electromagnetic simulations of your individual subsystems, like your cavities and waveguides and maybe the coupling regions and so on, and then write down a circuit theory like model for your entire system and understand what the properties of your entire system are. So that's the flavor of modeling that couple mode theory is going to be about. So the way we are going to do this modeling for our purposes is to first, so today I'll basically just go through a review of waveguides, which you might have seen, let's say a class on waveguide theory, maybe if you've done EE340, or you might not have seen that, so we'll go through that very quickly. And then from next class onwards, we'll start trying to think about what would happen if you have, let's say, a cavity interacting with a waveguide, right? Is there some simple model I can build that can allow me to understand the frequency domain as well as time domain characteristics of the system? Okay, so so let me start off with a very basic review of dielectric waveguides, right? Which is what we are going to confine ourselves to. And to keep things simple, I'm going to talk about, in today's review, I'm going to talk about translationally invariant waveguides, right? So waveguides which essentially look something like this. So you have some kind of a permittivity distribution, which is independent of one axis, let's say Z, and it depends on the other two axes, right? So X and Y, let's see, right? And in a typical dielectric waveguide, what you have is you have some kind of a high index medium in the middle surrounded by a low index medium, although you can have more complicated designs. And because of this particular choice of permittivity distribution, you end up confining light to the middle of this pipe, so to speak. But because it's translationally invariant in the Z direction, your electromagnetic modes can propagate down the Z axis, right? So a waveguide, a dielectric waveguide by definition, is essentially a permittivity distribution, epsilon, which only depends on X and Y and doesn't depend on Z, right? So as you might have seen in an electromagnetic class, when you start trying to characterize the modes of the structure of this waveguide, you end up writing your electric field modes. Because it is translationally invariant in the Z direction, you can assume a plane wave-like solution in the Z direction. And because it is a more complicated permittivity distribution in the X and Y direction, in general, you'll have to go through some more complicated techniques to figure out what the X and Y dependence are. But generally speaking, our electric field looks like some function of X and Y multiplied by exponential I beta Z, right? So this is what the mode of a waveguide looks like. This beta is called the propagation constant, right? And this is what we'll call a mode profile. Okay. And you can calculate these propagation constants and mode profiles by solving an eigenvalue problem, right? At any given frequency, you can calculate these propagation constants and mode profile by solving an eigenvalue problem that you actually get from Maxwell's equations, right? So all of this is described in great detail in the notes, so I'm not going to go through all of it in great detail, but maybe I'll make a few comments here. So this propagation constant beta is typically a function of frequency, right? So for a given frequency, your propagation constant is some function. This function depends on epsilon of x comma y. So you have some opportunity of designing this relationship by choosing a permittivity distribution. And at the same frequency, you often have multiple guided modes, right? So in a waveguide, just like in a cavity, you have multiple modes. Similarly, in waveguide, for the same frequency, you will have the lowest fundamental guided mode, first higher order guided mode, and so on. So we are typically going to index this by an integer n, which tells us which guided mode you're looking at, right? So this is, and corresponding to each propagation constant, you also have a mode profile exponential e of n, x comma y, and this essentially also depends on the frequency, right? So beta n comma omega is often referred to as the dispersion relation of the nth guided mode. Okay. Now, in general, this is a vector that has both x, y, and that has all x, y, and z components. Right? So even though this is a mode propagating along the z direction, right? So it's propagating along the z direction. Because this permittivity distribution is not uniform, the electric field is not going to be in the transverse plane. The electric field can have components in all three directions, right? But the components have a very specific phase relationship, which is important. So one point about the mode profile is that there is a very specific phase relationship between the transverse and longitudinal components. Right? So in other words, so one choice of E, so your En of x comma y comma comma omega essentially looks like some transverse field x comma y comma omega. This is only in the xy plane, right? So we have a transverse field component, right? So it's a 3 is a vector. So the transverse field components, and this is a real field. So this is, completely real vector field. It's not complex. Plus it has a z component, which is pi by 2 out of phase with respect to the transverse component, right? So this is.
What's the intuition of this equation?
Why is it pi by 2 out of phase?
Yeah, how do you derive this?
Yeah, so one very easy way of thinking about this is that this is just a consequence of divergence condition. So you have divergence of epsilon of x comma y times E of x comma y comma z has to be equal to 0, right? Yeah. So now your divergence condition you can write as the transverse divergence operator applied on the transverse electric field, right? And the z variation is simply exponential I beta z, yeah, right? Plus z hat times del by del z, right? Applied on z hat times z component. Does this make sense? So I simply wrote my electric field as some transverse field plus z hat times a field polarized in the z direction, right?
Where's the exponential I beta z?
Say that again.
Is it exponential I beta z component?
But that is because we are looking at propagating waves, right?
Oh yeah, yeah,
So
right.
the z dependence is always exponential I beta z, right? So now if you look at this, so all of this is derived in detail in the notes, so you can read through the notes for this. I don't want to spend too much time on this, but essentially this exponential I beta z with del by del z will give you an I here, and you'll be left with just EZ of x comma y, right?
Yeah.
So this is just coming from times the epsilon x comma y. This is just coming from the divergence condition. So you can see that these two have to be pi by 2 out of phase for you to be able to maintain divergence condition, right? So that's one way, one reason why this is necessarily true. Okay. So, right. So this is one important property of the mode profile. We're going to use this in a minute. And also when we come to properties of waveguide-based devices. And so the second thing that you could do is, of course, when we write this, solution as exponential I beta z, we are typically assuming beta to be more than 0, right? But that just means that you're only looking at forward propagating wave. For every forward propagating wave, you also have a backward propagating wave, right? So one question that you could ask is that given a forward propagating wave, how do I construct a backward propagating wave, right? So you could say that, well, is it just a simple matter of switching beta to minus beta? That is one guess that you could have. So if I have a forward propagating wave, is it just a matter of flipping beta to minus beta? But then if in general you're changing beta, then you would expect your transverse mode profile to also change, right? So you have to think about what happens to the mode profile of a forward propagating wave, as well as the propagation constant of a forward propagating wave, right? Also of a backward propagating wave. So if we want a backward propagating wave, so one way of constructing a backward propagating wave is simply by conjugating the forward propagating wave. Right. So if you have, in other words, if you have E, which is a forward propagating wave as a function of x, y, and z, I've written a plus here to indicate it's forward propagating, as some electric field, a mode xy times exponential I beta z, then you can construct a backward propagating wave as the conjugate of the forward propagating wave, right? And the reason why we can do conjugation is because if you're working with dielectric waveguides, the permittivities are real. So if electric field E satisfies Maxwell's equations, then its conjugate satisfies Maxwell's equations, right? You can just take Maxwell's equations and conjugate the whole thing, right? Because you can conjugate the whole thing, the conjugate is a valid solution of Maxwell's equation. So now I have my forward propagating solution, I conjugate it, and I ask myself, well, is that also a forward propagating solution, or is it a backward propagating solution? So the conjugation essentially flips exponential I beta z to exponential minus I beta z. So from a forward propagating solution, the conjugation operation gives you a backward propagating solution. Does this make sense? So given a forward propagating wave, I conjugate to get a backward propagating wave. And if your transverse field profile, if your mode profile has a transverse and a z component that are off by a factor of pi by 2, in the backward propagating wave, they're going to be off by a factor of minus pi by minus I instead of plus I, right? So you have some E transverse n xy minus I z hat en, en c as a function of xy, right? Because of the conjugation. Okay, so this is an important property, right? Because this is an important property. We are going to use it when we come to, trying to understand things like reciprocity and time reversal symmetry. Okay, and so maybe one last comment on this waveguide modes, and then we can move on to something more interesting. Is that you can also construct, well, corresponding to an electric field mode, you can also construct a magnetic field mode, right? So how do I do this? Well, I can just do it from the Maxwell's equation. So I know that del cross E is equal to minus mu naught del H by del T. And if I write this for frequency domain, which is what we're looking at, I just get I omega mu naught H, right? So which just tells me that H is equal to del cross E upon I omega mu naught, right? So if I want to construct the magnetic field corresponding to a mode, right, corresponding to E being E of x comma y exponential I beta z, all that I do is I use this equation and calculate H, right? So that is essentially all that I need to do. And I will leave for you to show this, or you can also go and read the notes, that if you do plug in this form of the electric field into this curl operator, and you use the fact that your electric field mode has a transverse real and an imaginary z component, what you end up getting is that your magnetic field H also has a transverse real, right? The mode has a transverse real plus an imaginary z component, right? So this just follows from Maxwell's equations, right? And then you can construct the backward propagating wave magnetic field by applying the same equation on the backward propagating wave. So you have H minus is del cross E minus divided by I omega mu naught. And again, if you plug in the form of E minus, which was E star xy exponential minus I beta z, right? What you end up getting is H minus ht of xy plus I z hat hc of xy, okay? So all of these seem like details, but they're very important. So that's why I'm going through them here. So note, so just to recap, okay, so let me recap here what I just said in the last 5 minutes. So you have a waveguide, and you have a mode which has a transverse component that is real for a forward propagating wave, and it has an imaginary component which is along the z direction, okay? For the backward propagating wave, you have, so this is for the forward propagating wave. And the magnetic field has a very similar structure. So it has a transverse component which is real, and it has a forward or a longitudinal component that is imaginary. What about a backward propagating wave? So for a backward propagating wave, you have a transverse field which is real, and you have a longitudinal field which is imaginary, but it is pi by 2 out of phase with respect to the field of the real mode. And the magnetic field has a negative, it has a transverse field which is pi out of phase with respect to the forward propagating wave. And it has a z component that is in the same direction as that of the forward propagating wave. Okay, so this is one particular choice of your waveguide mode. Of course, if you choose the waveguide modes to be different, if you can always add phases that you like, or you can multiply them by constants, and you can get a different choice of the waveguide modes. But this is one concrete choice that we can make, and so we're going to work with the choice later on. Okay, so this is very, very rough description of what waveguide modes look like. Now, just as in cavities, we saw that you had orthonormality between cavity modes, you similarly have orthonormality in waveguide modes as well, right? So two waveguide modes are independent of each other, right? Two different guided modes are independent of each other. So if you take two different guided modes, right? So which is two different solutions of Maxwell's equations. Right? So what you can then show is that the following orthonormality relationship holds. So you have z hat dot the transverse components of the nth mode as a function of x comma y cross the transverse component of the mth mode of the magnetic field as a function of x comma y dx dy half is equal to delta m comma n, right? So this also just follows from Maxwell's equations. And this is telling you that there is independence, there is some kind of an inner product that you can find a form between the transverse components of the different modes, so that when you apply this inner product, the inner product goes to 0 on different modes. If you apply it on the same mode, it goes to 1. But if you apply it to different modes, it goes to 0, right? So this is the corresponding orthonormality of guided modes. Okay, so these are things that you would have again seen in detail in waveguides class, in the waveguide theory class. If you have not, the very careful derivation of all of this is in chapter 3, first section. So I encourage you to go through that if you're unfamiliar with this material, and we can talk about it in office hours. Okay, so now let me come to the more relevant portion for us, which is scattering matrices in waveguide-based devices. Okay, so the kinds of devices that we are going to be generally interested in is that you have some kind of a cavity sitting here that you could have like a system of cavities which you've made out in some kind of photonic crystal, or with ring resonators, or whispering gallery modes and so on. So you have some system of cavity modes, and you have some system of waveguide modes that are interacting with the system of cavity modes, right? And what you're interested in understanding is what do the spectrum of the system look like, right? So if I shine in, let's say, light at frequency omega through one of the waveguides, what is the light coming out through a different waveguide at the same frequency, right? So can I say something about the transmission spectrum or reflection spectrum of this, coupled cavity waveguide system, right? So in some sense, what I can do is, just from a perspective of waveguide-based devices, I can deduce some very general properties of what this transmission look like, right? So so to speak, the scattering matrix in between these waveguides by black boxing this permittivity distribution in the middle, right? So I can just think of this as a device that has input ports that are the waveguides, the forward propagating modes of the waveguides that are bringing energy towards this region. And I can consider this as a device that is scattering some modes into the backward propagating modes of the waveguide, right? So I could think about, let's say, describing these waveguides with some amplitudes of forward propagating waves. So, let's say B plus 1 of omega, and some amplitude of the backward propagating wave. And let's say you have total of n ports, so to speak. Right? Sorry. Right. So where we are assuming, forward propagating waves are modes that are going towards the device, and backward propagating waves are modes that are coming outside the device. And then, sorry, say that again.
Sorry, inside the black box, can we, is that a complete solution to express the solution inside the black box as a function of several waveguide modes?
No, not in general. This is only true inside the waveguides.
Then
so inside the black box you have, so this is only in the region outside the box.
Yeah.
So what we are,
Yeah, maybe you can continue.
Yeah, so the fields inside the box, of course, can be very complicated. They can be almost arbitrary. What we are saying is that outside the box, if you assume that your device is designed in such a way that it is scattering into the waveguide modes, right? So the field outside the box can be written as a sum of forward and backward propagating waveguide modes in different waveguides. But you're absolutely right that this is no longer a basis for inside. But you'll see that when we are trying to understand general properties of the system, what we'll only need to know is what happens on on a surface enclosing the device. So a lot of properties of the system can be deduced by surface integral forms of Maxwell's equations. So they don't really care about what's happening in the volume, they just relate electric fields on the surface. And then this guided mode ansatz is completely fine, because we can choose a surface to only intersect the waveguide and never really go inside the box. Okay, yeah, but you're right. Inside the box, it's more complicated, but we are choosing to black box it for now, not really think about it. Okay, so right, so you can think of this like as an N port system. So I have N input port that I can shine light through, and I can get N light out from N output ports, and then I can relate these input and output ports with a scattering matrix, right? So this is one key definition. So we are going to define our scattering matrix as. Okay, I think we're out of time, so I'll just write this down and then we can stop for today. As a matrix, this will be an N by N matrix, which relates the fields that are going away from the device with the fields that are coming in the device, right? And you could imagine that you can, in general, calculate the scattering matrix through electromagnetic simulations. You could send in one waveguide mode at a time and calculate how much fields are coming out in all the other waveguide modes. And this will give you access to each column of the scattering matrix, right? So the scattering matrix is something that you can compute, right, by solving Maxwell's equations numerically, for instance, right? But what we would do in the next class is say that, even if you don't really think about solving Maxwell's equations, there are three properties of the scattering matrix that you can expect to hold just because of the fact that the fields inside solve Maxwell's equation. So those three properties are going to be unitarity, which comes from energy conservation, symmetry that comes from reciprocity. So this is reciprocity, energy conservation, and conjugate inverse, which comes from time reversal symmetry, right? So three very general properties are going to give us three properties of these scattering matrix, right? And then when we actually look at couple cavity systems or cavity waveguide system, we'll see that if we just restrain ourselves to maybe not satisfy Maxwell's equations exactly, but satisfy these three more general properties of reciprocity, time reversal symmetry, and energy conservation, we can already tell a lot about what the spectrum of our systems is going to look like. So the spectrum, like you see a Lorentzian in cavities, or you see like, splitting in couple cavities, it's not really a consequence of Maxwell's equations, but rather can just be deduced by these three very simple and general properties, right? So you don't really need Maxwell's equations in specific, but any physics satisfying these properties will give you those spectral features, right? And which is, of course, maybe one of the reasons why those spectral features come everywhere in physics and quantum mechanics. It doesn't really matter if you're doing E&M, but that's kind of what we are going to study over the next few classes. Okay, so I'm going to stop here. I think we are out of time. So yeah, so I'll see you, I guess, next class then.
Is it how can we know the beta depends also on X and Y?
Beta? B.
Yeah.
Here?
B. The propagating factor.
That's a constant. That's just a constant.
So it just depends on the frequency, right?
Yeah, exactly.
But you also
it depends on the permittivity distribution. So if you change the permittivity distribution, a propagation constant changes, but it's not a function of space, right? If you use a circular waveguide instead of a rectangular one, for example, you'll get different propagation constants.
Oh, okay, yeah.
Right, or you change the refractive indices, you change propagation constant. That's what I meant.
Yeah. Okay. Thank you.
Okay, yeah, great.